Today we are discussing Boyle's law as postulated by Robert Boyle in the 17th century. It states that the volume of a given mass of gas is inversely proportional to its pressure at constant temperature. That is to say, V is inversely proportional to P, V representing volume and P representing pressure. That is to say that V is equal to K over P, and K is a constant of proportionality. So we see that a product of P and V is constant. Now we can use these diagrams to explain Boyle's law. We have the gas in the cylinder there, represented by V, and we have the weight on it, is the pressure. Now we see here that when the weight is doubled, the volume, that is the space occupied by the gas, is reduced by half. So we can also say that this other one, the volume here is V1, and the pressure, that is the mass or the weight on it, is P1. Yeah, the volume is V1, the weight is P1. So now doubling the weight now is P2, which makes V2 now to become half. Yes, we can as well represent this law graphically. When we plot P against V, we get this kind of graph now, as you can see, is inversely proportional to V. So that is why the shape of the graph is like this. So we can also have it this way, that when we plot P against inverse of V, that is when we have a straight line graph that starts from the origin. A third way of representing this law graphically is also like this. So in all, we see that P1 V1 is equal to P2 V2, which means that when we take a product of P1 and V1, it will also be the same as the product of P2 and V2. The same goes with P1 and V1 equal to P3 and V3, and so on. We can as well use a diagram to represent this. As we can see in this diagram, P and V are inverse, which means when you have the higher value of P, you have the lowest value of V, and vice versa. Now, let's consider the kinetic theory explanation of Boyle's law. The gas pressure, as we have said in an earlier video, is due to the bombardment or collision of the gas molecules with one another and with the walls of the container. Now, since the temperature is constant, it means that the average kinetic energy of the gas molecules is constant, which means that if the volume or the space occupied by the gas is reduced, it means that the gas molecules have a shorter distance to travel, which means that they will now be colliding more often with one another and with the walls of the container. That is why that reduction in volume or space results in an increase in gas pressure. Now let's have an example on Boyle's law. A sample of argon at STP occupies 0.90 dm³. What volume would it occupy at 510 millimeter mercury at the same temperature? We see here that the first pressure, P1, is 1 atmosphere. Of course, atmospheric pressure is 1 atmosphere, which is 760 millimeter mercury. V1 is 0.9 dm³. P2 is 510 millimeter mercury. That shows that the pressure has reduced. So we expect the volume to increase, and we're looking for V2. So we use this formula, and making V2 the subject of formula, we have it this way, that 760 times 0.9 over 510, which is P2. The answer gives us 1.34 dm³. That shows that as the pressure reduced, the volume increased. Let's check a second example. A sample of nitrogen at 1.0 exponential 5 Newton per meter squared occupies a volume of 300 cm3. What would its new volume be should the pressure be increased to 2.5 exponential 5 Newton per meter squared at the same temperature? Now, of course, we have P1 as 1.0 exponential 5 Newton per meter squared, and V1 is 300 cm cube. We also have P2 as 2.5 exponential 5 Newton per meter squared. So we're looking for V2. Using this formula, I'm making V2 the subject of formula, then substituting, we have it that V2 is 120 cm cube. This shows that as the pressure increased, the volume reduced. Thank you very much, and watch out for Charles' law.